And up next, we have Waffle. It's on the compiler team working on explicit tail calls, the never type, and more. And they're working on tasking the company on a new Rust C backend for the automotive industry. It co-created the unfair Rust quiz, which you should all try, which you can find if you Google for it. It's very easy. And it recently acquired a witch's hat, which you can see.
Okay, so MC already introduced me. I will just quickly say, this is my avatar on GitHub. It's adorable. Quickly, the outline of the talk. I'll talk a little bit about what trait objects are, just so that we're on the same page. Then I'll talk about the layout constraints, how you could implement the trait objects based on how Rust works. Then I'll work on a simple implementation. Then we will move to advanced features. They're not really advanced, but they're harder than just base trait objects. And finally, we'll talk a bit about optimizations, how you can make it even better. So what are trait objects? I think it's best to look at an example. Consider we have a trait. It has a method that returns something. You then implement it for an integer, for example, or any other type. It doesn't matter. And then what you can do is you can coerce a reference to an integer, to a type that implements the trait, to a trait object, to a reference to a dean trait, what is called a trait object. And then you can call methods on the trait objects the same way you would be able to call them on the original value. The nice part here is that you can do it with other types too. You can replace the integer with a unit or any other type. And then you could still call the method on the trait object, but this time it will call the underlying function for unit, or the underlying type that is behind the trait object. So it's type erasure, basically. The takeaways: if a type implements trait, then you can coerce a reference to a type to a reference to a trait object. You can call methods of the trait on the trait object, and it will forward them to the underlying implementation of the type that is behind the trait object, which is determined at runtime. And for this to work, the trait object needs to store some kind of metadata, some information to find which function to call actually, right? What is the underlying type? And now let's talk a bit about the layout constraints, how you can lay out it in memory. And I think it's also best to see an example. For example, we have an array, and we have a reference to the middle of the array, to one of the elements. In memory, it will look something like this. We have the three integers of the array right next to each other, and then a pointer right in the middle of the array. Well, if we change the type of the variable which is pointing inside of the array to a trait object, well, we will need to store the metadata somewhere. A logical starting point would be to put the metadata right next to the value that is being pointed to. So something like this. But that doesn't work, because you can't change the array, right? It's an immutable variable, or it could also be a static variable, or anything else, right? You cannot change it necessarily, and you can't change it in this example. So what you have to do is put the metadata somewhere else. And well, there is not many options. One of the only ones is to put it inside of the reference, right? To make the reference bigger, wider. And now it consists of two parts. It consists of the data pointer, which points still to the first element of the array, or the second one, whatever. The one with the index one. And the second part of the reference is the metadata, which allows us to call the method. And that works. But maybe it has some issues. Here's another example. Trait objects don't work only with references, but they work with a lot of different kinds of pointers. They work with boxes, arcs, RCs, row pointers even. So in this example, we have a box which wraps an integer, and then we convert this box to a trait object. And it works kind of in the same way that now the box is also multiple parts. And in this example, we'll also drop the box, right? We run its structure. And if we look into the implementation of drop for box, we will see that it actually needs more metadata than we have so far, right? To properly deallocate a value from heap, you need to know its layout, the size and the alignment. And also, another thing that box does is it runs the destructure for the value, because you don't want leaks or anything. So what we would end up with is a lot more metadata. We have still the data pointer, which points to 1, and then we have the method, the size, the alignment, the drop implementation. Well, that's 5 things, and moreover, that's 5 pointer size things. That's like equal to 5 view sizes. It's pretty big, especially, and that's a problem, because you often pass values as arguments to functions, for example, and if you pass big objects, you will quickly run out of available registers. So you will have to use stack, which might be slow. But if you notice, all the metadata parts are not dependent on the concrete value that we are pointing on. They only depend on the combination of the underlying type and the trait, which is the trait object trait. So what we could do is move the metadata to some static variable, some static memory, and then only store the pointer to this metadata in the reference, or the box in this case. Well, yippee! This works. This just works. It's notable that Rust is uncommon in the way this is implemented. Most other languages which have vtables actually store the virtual table with this metadata of everything near the object. But the reason they can do it is that they usually have a closed set of things that can be in a vtable, right? There is a set of interfaces that you implement, and you can't change it outside of the type definition. But in Rust, you can implement kind of any trait for any type if it's coherent and stuff. So you don't know the full vtable at any point until like the near end of compilation. So you need a specific separate vtable for each combination of the type and the trait. So that's why we needed to do it like this. Now let's move to more interesting things, maybe. Supertraits. Again, example, we have the same trait, but now we add a supertrait. And what that means is that when you implement trait, you must also implement supertrait. In this case, the supertrait has only one method, it's meow. And we can call a method of a supertrait on a subtrait, on the subtrait trait object. So in this case, we have the same a, which is a trait object of trait, and so on. And then we call meow, so the method from the supertrait. And one way to do it is to include pointer to the supertrait vtable, to the supertrait metadata, in the vtable of the subtrait. And so now if you want to call meow on a dn trait, you would first load the vtable pointer to go to the vtable of trait, then load the another vtable pointer to go to the super vtable, and then there's meow and you can call it. Of course, this is kind of an underlying thing that is hidden from the users. This is just compiler stuff, but that's what we're exploring right now, the underlying implementation. That works. So, but that is kind of inefficient, right? To call meow, you need to follow two pointers, right? You need to follow to one vtable, then another. And if you have like a supertrait of a supertrait of a supertrait, it gets annoying. It gets slow. So what we can do instead is notice that to call meow, you only need the function pointer to meow. You don't need, well, you have all the other metadata already in this vtable. So instead of having a pointer to the super vtable, we could just include the method here. And that worked nicely and leads us to kind of smaller, maybe memory footprint, but not really. Now, I think like one of my favorite things here is trait object upcasting. Probably because I worked a little bit on it, but I do think it's a cool feature, right? If you have a trait object, what you can do is coerce it to a trait object of the supertrait. So now you just have the trait object of the supertrait. And then again, you could call a method of the supertrait, but you couldn't call the method of the subtrait because the vtable for the trait object of the supertrait only contains methods from it and its own supertraits. Okay. So the way we could do it is return the virtual pointer, right? Return the pointer to the supertrait vtable in our traits vtable. And now we can still call meow with only kind of one dereference. We only need to go to our vtable. But if we want to go to supertraits vtable, we can also do that and store it somewhere and use that. And that works quite nicely. But can we do better? If you look closely, side to side, on the vtables of the trait and the supertrait, you can notice that they have a lot of overlap. In fact, like 4 entries are just the same. So what if we rearrange them so that the supertrait vtable is just a subset of the traits vtable? Well, what we could do then is to go to the supertraits vtable, you just offset the pointer, right? You just ignore the first entry, which doesn't matter for the supertrait, and you get a supertraits vtable. What? Oh, right. I typoed in the presentation it said offset 2 instead of offset 1. Oops. But if we reverse the order, instead of offsetting, we could just do nothing. Because if the vtable for the subtrait starts with a vtable for a supertrait, then a pointer to it is also a valid pointer to the vtable of the supertrait. Because, well, it will just ignore the last entry now. And that works kind of automatically because you just don't go there. That's cool. This is actually what REST does. and I think it's very cool. Now, what if we have multiple supertraits? Another example, here we have like a trait D, and it has 3 supertraits, A, B, and C. So A, B, and C are supertraits of D. Well, if we do what we did before, of kind of inlining the vtables of the supertraits into the subtrait, you get this. And it's okay, I guess. But you have a lot of duplication. Like the drop size alignment needs to be duplicated. And also, you can still go to the first supertrait doing nothing, but the other ones still require an offset, at least. I know. Oh, wait. Yes. Well, psych! Remember virtual pointers? Well, we could use them to get this. So now we still inline the first vtable, first supertrait vtable, because that one can be optimized nicely, right? It doesn't cause us any waste, and it just works. You can use identity cast to go to the vtable. But instead of inlining other supertraits, we just include the pointer to their vtables. And that way, everything works quite nicely, right? You can topcast to the first supertrait, you can just do nothing. Topcast to others, you still need to load a pointer, but you still need to do something in that case, so it's not kind of avoidable. And you can still call all functions from the supertraits quickly. And again, this is how RST does it. This is kind of the actual layout of a vtable, and I actually checked it with the compiler just to be sure that I didn't mess everything up. I didn't have time to prepare things for all the things. Oh, to prepare slides for all the things. So you will not have any more slides. Traits without methods never need virtual pointers, because if a trait has no methods, its vtable is just drop size and alignment. And drop size and alignment is part of every vtable. So yeah, traits without methods can kind of be ignored for the layout of the trait objects. Another thing is resolved or missing entries. Sometimes, okay, let me see. It will be hard to understand without slides, but I will try. I should have thought about this before. So, if you have a trait and you have a method inside of it, you can still curse it to a trait object if it has certain where bounds on the method. For example, if it's send, right? So for example, you can have a trait method and a where bound on the method saying if self implements send, right? And then you can still implement this trait for a type which doesn't implement send, but you couldn't call the method. So in this case, the vtable still needs to keep the same layout, because of course, if you have a vtable, you don't know anything about the underlying type. You can't check if it implements send or not. You can sometimes guarantee that it implements send in case if you have like din trait plus send, then you know it's send. But if it doesn't have plus send bound, you don't know if it implements it or not. Or if it's just like a trait object which doesn't say to you that it implements send. So in those cases, the vtable will have just like an entry which contains a null pointer. It doesn't say anything. Okay. Conclusion, trait objects are cool. I like them. You should too. Okay, thanks, bye. I think we have a bunch of time for questions, so I'd love to hear them.
Yes, there's a bunch of time for questions. So,
hi. So at the moment, traits can have associated constants. Could you store those constant values in the vtable?
Yes.
Does anybody is this something that RustC does or could support?
No. I mean, it could support it. It doesn't, and there aren't any proposals that are being worked on for this.
next question. There. It's hard to see with the lights.
Thank you. These features that allow you to cast between supertraits and subtraits, are they compiled into the binary conditionally on if you actually do that, or are they always present in the binary whether you do the casts or not?
No. Okay, so they're compiled always, because at the time that you're emitting the vtable, you don't know if it will be used or not, right? For this to be conditionally compiled in, you would need like whole program optimization, which is its own kind of worms. If you're concerned about the fact that having those virtual pointers to the supertraits makes the binary bigger, well, we did the measurements. It doesn't matter, like literally in any case. It's very hard to make a pathological case which will grow the vtable a lot. And even in this case, the vtable must be big in the first place. So like the percentage difference is not that big. So there is no downside, basically.
Okay, thanks.
By the way, I forgot to say this, but the trait object upcasting was stabilized very recently in the last release, so 186. This was like the third attempt to stabilize it. Yeah. Yeah, it's very cool.
Yeah, congratulations on that.
Thank you.
My question is, you showed an example where there's 3 supertraits, A, B, and C.
Yes.
And the vtable of A is inlined. Is that always the first trait object in declaration order, or does RustC do something clever, like it notices that you actually upcast to A and wants to make that upcast cheaper?
Well, again,
That one.
you can't notice the upcast because that would require whole program optimization. It's currently always the first in declaration order, but of course, all of those layout, it isn't guaranteed, right? It could be literally anything, but currently it's the first one. And then also like the first supertrait of the first supertrait, of course.
Right, yeah.
Yeah.
So we as programmers can actually make use of that implementation detail for a tiny, tiny micro optimization if we want to.
I guess so, yes.
Thanks.
So if I have a function that's only used inside of a trait method, could that be, because then like, because that can't be optimized away if the function is part of the vtable, correct? Would that be a possibility where like there could be larger sizes of binary saved?
Let's see. Possibly, maybe, I know. So to properly optimize this, you need linker time optimizations so that the linker can notice, hey, you're not referencing this vtable actually, I can remove it, and then you can notice that you're not using functions anywhere except this vtable, so it can remove those also, in theory. In practice, I noticed that RustC is bad at removing that code sometimes, especially like that code in the sense that functions which aren't used. Sometimes it's bad, especially like for trait functions. And linkers are sometimes good, sometimes not, so I know. We need better everything.
Interesting. Thank you.
Does anyone have another question? I have a question.
Yeah.
So this is sort of tangential, but so you have DIN compatibility is a concept, right? Which is an entire grocery list of requirements that you need to meet to be able even to declare something DIN. Do you know of any efforts to release those constraints a little bit more?
So you cannot really do that. I mean, the constraints are almost as loose as they can be. The only thing that can be loosened is maybe allowing constants, what was the first question I think about. And as I said, there aren't current efforts to do that. And for everything else, it's basically like a hard requirement, I guess. Like the thing that the incompatibility kind of tries to provide to the compiler is the guarantee that kind of all functions are either not callable through a DIN trait, for a trait object, or they accept a self-argument so you can actually get the vtable and know what exact function do you need to call. And there isn't any other mentions of self such that kind of depending on the self type, the ABI would change. So yeah, there isn't really much space to lift restrictions.
Okay, thank you.
Mm-hmm.
Anyone have a question? So I guess that's it. Give a great hand of applause to Waffle.
Thank you.